For every problem, there are like a million ways to implement it. And one of the best ways to learn software engineering is to look at how others solve different problems. Hi, I'm Yvette Erdog, and I've been facilitating Coderetreat events for about 10 years and fairly regularly. So over the years, I have seen over 100 different solutions to the same problem, and all of those solutions had some unique quirk, and I learned a lot from them. But today I want to bring you 3 of these interesting solutions, and also the basic one that everyone starts with. And my goal with that is to help you gain new perspectives on what code can look like and maybe learn something that you can use in an upcoming project soon. So what is the theme? At Coderetreats, we get together and implement the same one single problem, game of life, over and over again. And that gives you an option to really experience how different these solutions can look like. So I'm going to also look at this very simple problem. So let's start with defining what game of life is. Game of life is a cellular automata that starts on a grid. It's a square grid. And on this grid, you might have cells that are alive. I will mark them with this pink color, and cells that are dead. Everything else right now is dead. And then we have a bunch of rules of how you can get from one state of this world to the next state. And I will tell you the rules now. What I want you to do is pay attention to the cell in the middle, the one that is in a rectangular white border, because this is the one for which I'm explaining the rule. So if there is a cell that is alone, it's going to die. If there is only one neighbor for that cell, it's also going to die. But if there are 2 neighbors, then it will stay alive. It will also stay alive if there are 3 neighbors to that single cell. And then the next rule is about 3 neighbors. So you have something that is not alive, and then if it has 3 neighbors, then it will become alive. And finally, if there is a living cell with more than 4 neighbors, it's going to die. So these are the rules of game of life. And it's a fairly interesting problem because when you implement this, it actually starts making these really interesting animated patterns. So this is one example of a game of life where we just look at subsequent states of this infinite grid. So this is the problem. I'm not going to worry about implementing the visualization. We are just worrying about the actual code that takes the input, the representation of the world, and creates a new representation. But that begs the question, what should be the data structure? So most people, when they look at this problem, they come to the obvious conclusion that the data structure should be a matrix. And yeah, why not? Let's try it with a matrix. Although it does violate the rules a bit because in game of life you should have an infinite world, and this is creating a finite world. But I'm gonna let that slip for now because everyone does, and their first solution is going to be just starting off from a matrix. So we have this function that will take this 2-dimensional matrix and it will convert it to the next representation of the world. And how do we do that? Well, first, the very naive solution would be to start with a new world. It's an empty list. We are just going to go through all of the cells of the old world. And for each cell, we decide if it's alive or not. We use this should_alive function for that we are going to implement in a second. And we just add the cells one by one with alive and dead as the 2 possible values. I did skip the part where I defined these constants. Alive is 1, dead is 0. Okay, let's move on next. Then we need this should stay alive function. How do we do that? Well, we count the neighbors. Let's assume we already have that function. And then we just have this if statement, or return value of, okay, if there are two neighbors and the cell was alive, then it should stay alive. And also it should stay alive if there are three neighbors, but it should also be alive if it wasn't alive and it has three neighbors. So this really simple expression will do that. Okay, how do we count the neighbors? Well, we have a for cycle that goes through this 3x3 area, and then we check if that cell is alive. If it's alive, then we add it to the count, and in the end, we subtract the middle one because that's not a neighbor, but we added it because we didn't want to add one more extra if statement in there, and that's it. And if we do that, then we get this fairly long solution, and this is actually going to be one of the longest solutions today. And basically, if you ask ChatGPT to do something like that, it's probably going to return this or some similar implementation, and quite honestly, it's boring and it has a lot of drawbacks. It's just what a junior developer would do. So let's do it the way grown-ups do it. So the first solution I want to show you has to do with a non-existing sequel of the matrix, which is the function. And the reason I'm saying that is because in this solution, our data structure will be the function. We are not going to have any data structure indeed. We are just going to have a function that represents the world. And this sounds weird because, I don't think, when I think of an array or a matrix, I don't think of a function. But if you think about it, of course, in most languages, the syntax is different. But in the end, when you say, I want to take the value x and y from an array, what you're really saying is that you have this function that will return the element of the array at that position. So actually, an array is kind of a function. So let's just use that abstraction and not worry about the particular implementation. The weird consequence of that is that suddenly our world is infinite and we did nothing. Strange. So how do we do that? Then we need a evolve function, and this time this is going to be a higher order function. It's going to take a function which is our representation of the world, and it's going to return a function which is the representation of our next generation. That's starting to get mind-bending for those of you who are not experienced in functional programming. The functional programmers amongst you are probably just saying, yeah, sure, that's what we do usually. Okay, so let's get a couple of definitions out of the way so that it's easier to write the remaining part of the code. That is going to be 0, alive is going to be 1. I'm going to add this sum function to the array prototype, which is just summing up the elements in an array. It's going to be convenient later on. And I will also create this deltas constant. I could generate it like this, but maybe it's easier if I just write it out like this. This is basically just a 3x3 list of neighbor differences. So these are the 8 values that you should add to a vector of two-length vector to get the neighbors. And the reason I want to do that is because I want to be able to for cycle through the neighbors of an element. And this is going to be useful for that. Okay, so now that we have all that, we need this higher order function that gets a world, which is a function, and then returns the next function or next world representing next function representing the world. Okay, so how do we do that? Well, we start out by returning a function. That's going to be our end result. So why not start by just returning a function and figuring out what goes into it? This function is representing a world, so it has to return alive or dead. Straightforward. Okay, then when does it return alive? Well, it returns alive if the neighbor count is 2 and the cell was alive, or the neighbor count is 3. How do we know the neighbor count? I will do a map. And the map is going to just take the XY coordinates that were fed into our function and then adds the delta to it. So now we have a list of the neighbors. If we have a list of the neighbors, then we can apply the previous rolled function to this list, which is really nice, because now that we can apply that, we only have to sum this up. Because if we sum this up, then we suddenly have the number of cells that were alive in the previous generation. And that's it. Fair warning about this solution. It uses tons of memory, but at least it uses that lots of memory to run really, really slow. So it's not very efficient to use it. But interestingly, did you notice that there isn't a single for loop or if in this code? Like no structures at all. This is purely strings one after the other, which I think is a very interesting solution. It's also a very clean and easy to understand code once you get your head around the idea that your rolled can be a function. And if you think about it, one of the functions that you could pass in is just a function that accesses elements of an array, so that's not that big of a difference. Okay, so I love this solution. It's mind-bending at first. If you haven't been doing functional programming before, I'm pretty sure that this solution is going to be one where you scratch your head for a while. But also, it abstracts away the data structure, so you could use anything. This could be a matrix like before, or it could be just a list of living cells or a set of living cells, which is quite interesting that you can create an implementation that has nothing to do with the data structure underlying. But what I don't like is the next sequel. No, not that one. I actually like that movie. This one, MySQL. So here's the thing about MySQL and about SQL in general. It's very good technology. It's great technology for the purpose it was designed for. It was designed to give access to non-technical people to data. Semi-technical people. At the same time, we ended up using it as a proper production database language, and I think it's not the best for that, but it's very powerful. That much I have to give it. So anyway, since I don't like working with SQL, and I usually try to use other database types, I did the most obvious things I could, and I tried to implement Game of Life in SQL. So how do we get started with this SQL solution? The way we get started is we have this population table, and this population table is going to have X and Y coordinates, and then we will fill up this table with the cells that are alive. And I will then populate it with a simple example of a state. So here we have 5 cells that are alive, and they are inserted into these values. Now I will also need a kind of a helper table. In other SQL dialects, you might be able to do this without creating a table, just somehow incorporating this into your query. But in MySQL, the easiest way is to just define these offsets. And this is the same that we defined with the previous solution as deltas. This time it's in a table called offset. Okay. Now that we have that, then what we could do is do a select from population offsets. So this is a join, a direct join of the two tables. And what I will do is just add the x value to the dx. Why is that important? So what this does is now I have a list of the neighbors of living cells with multiplication. So if a cell has 2 living neighbors, it will show up in this query twice. And then what I can do with that is I can do a group by and count how many times each cell showed up, which is nice because now I have all the neighbor counts. And of course, that's something we will need. Okay, how do we move forward? So the problem is that now we have the neighbor counts, but we don't know anymore which cells were alive. So I actually have to go back and modify this offsets table a bit. So I'm going to add this extra column to the offsets table, which is neighbors. And neighbor is going to tell us if a specific offset is representing a neighbor or it's representing the cell itself. And now we have not 8 but 9 values in there, and the extra value is 0, 0, 0, which represents the middle point. And now that we modified it like that, now I can add another sum, which is going to tell us if the cell is alive. And now we have this nice result, and from here it's actually not that difficult, right? If you're fairly new to SQL, you might be tempted to put this into a subquery. But those of you who are fancy people and know SQL a bit more, you can use a having clause, and you just say in the having clause you just specify the rules for a cell staying alive, and that's it. It's done. There is a catch. The catch is that this is calculating only one generation, and from a table we went to a different data structure, which is an output. You would have to repeatedly run this query manually to get multiple instances, and that's not nice. I would want to be able to run this multiple times. So how can we do that? So it turns out that SQL can do recursions, and you could write this query on the screen, and with the recursive, you should get you should be able to get a result set where you tell it how many generations you want to generate, and then it will just return multiple generations. There is one problem with this, and it doesn't work. And it doesn't work because we will get this weird error message. Aggregations and window functions are not allowed inside a recursion. Damn it. So this is MySQL specific, by the way. But unfortunately, this query, although it looks like it should work, it doesn't work. But there is this window functions. What is window function? Like, I started thinking, okay, I went down the rabbit hole, looked it up. It turns out that window functions are really useful. But like, they are not very powerful in MySQL, but in PostgreSQL, you can use window functions. And if you go deep down the rabbit hole, you will figure out that there is this solution. I'm not going to explain this one. This is a horrible long code and it's hard to comprehend. But what this does is exactly that. You do a select, you tell it how many generations you want to generate, and it will just return a number of generations from the game of life. So why is it interesting? This is interesting for multiple reasons. One, I never knew you could have recursion in SQL. Fun to know. And I suggest you look it up. It's a good learning to see how this work. And then there are window functions, which is, again, very interesting. I'm not going to go into it because it could be a talk on its own. But I encourage you to just look it up because it's interesting. And then there is this idea of being able to do very complex stuff to data in the database, which is cool. Like, this means that you can bring certain types of calculations close to the data onto the database server. Fair warning, that also means that you can bring business logic closer to the data. Why is it a problem? Well, multiple reasons. One, you have one database, and if you overload the database, then it's really hard to scale. So it's not necessarily a good idea. The other thing is, once you do that, it's a lot harder to debug. Like debugging proper application code is much easier than debugging SQL queries. So it's cool that you can do it, use sparsely. And then finally, I want to show you one more solution, which I called Unleashing the Monster. And the reason I called it that is because it has to do with the GPU. Now, if you have any good computer or phone or whatever, you do have a GPU in it. The GPU is a very specialized computational unit. What it can do is add or do calculations in parallel. So let me explain that with an example. So when you want to add two vectors on a CPU, what you do is you add the first two numbers, and then you add the next two numbers, and the next two numbers, and so on until you have the entire array added. But with a GPU, it's a different story. In a GPU, you have the numbers, and what the GPU is going to do is it's going to assign a separate core or thread to each of these pairs of numbers. So instead of doing it sequentially, it just adds everything at once. And by the way, that is exactly why it's useful for graphics, because in graphics, you want to calculate pixels, and like calculating every pixel one by one would take a long time. But if you essentially have a separate core for every pixel to be calculated, it's very, very fast. And these, to be fair, these cores or calculation units are much simpler than a CPU, and they work in unison. They have to do the same thing, every single one of them, just to different data. But this architecture enables a lot of things in our world today. The whole blockchain thing was running on GPUs. The AI systems of today are trained on GPUs. That's why NVIDIA's stock prices are going up and up and up. So it sounds like a technology versus learning. Now, the problem is that when you want to program the GPU, you have to do that mostly in C++. It's an extension language of C++ called CUDA. And you don't necessarily want to learn C++, but there used to be this nice little library called GPU.js. Unfortunately, it's not working anymore, but it made it really simple to create GPU code in JavaScript. So I'm going to show you, to be fair, you can't really reproduce this anymore. Unfortunately, the GPU.js project got its last commit 2 years ago, and a few days ago when I tried to use it again, it didn't work anymore. Anyway, but with GPU.js, what you could do is you could create this kernel, and a kernel would take a Lambda function, and it will get parameters passed into it. And the nice thing about it is that there is this implicitly passed thing in this Lambda, which is the thread X and Y values. And the set output is going to tell the GPU what size of matrix should it calculate, and then each of the cells in the matrix will get a separate core, and each core will run this function separately, and the only difference is going to be the thread X and thread Y values. And basically, you could do this. You could just say that you are adding two matrices together, two n by n matrices, And that's how you do that with GPU.js. Okay, so if we go back to our first solution where the world was a matrix, then we could use the GPU to make this calculation. And basically what we would do here is just remove that outer double for loop and use the GPU instead, and calculate everything in parallel. So you have this kernel. You of course, and in the end, the kernel needs to return alive or not. Unfortunately, it wasn't possible to use constants here anymore. So 1 is alive, 0 is dead. And then we need to find out the count and the is alive. For that, I have this little for loop, just like in the first solution. This is basically the same thing, going through the 3x3 neighbor area and then just subtracting the middle cell if it's alive to get the count. And then we have this is the live function, which is needlessly complex because the GPU is very sensitive to getting out of bounds. So we do need to check everything very precisely if we are allowed to access a value. Otherwise, we're just going to return 0. And that's it. Now, this solution is interesting, and the reason I like it is because it's very powerful. Like, this is the GPU solution is the only one that can run in real time. All of the other solutions that I showed you are, it's nice game, but this is the one that you could use to generate actual game of life footage. And I also think that the GPU is still an underappreciated tool. Like, the people who use it are the people who really absolutely must use it. Those who deal with graphics, those who deal with AI, those who deal with NFTs and blockchains. But in reality, I think there are a lot of more problems that could benefit from this kind of calculations. So I think it's worth at least once trying what it feels like to code on a GPU, because at some point it can be useful. And also it's addictive. I really enjoy coding on the GPU because it's a different mindset. You always learn something new while doing this. Fair warning, GPU programming is addictive. And you can end up wasting a lot of time playing around with GPU. And it's really painful to debug. Unfortunately, when you are running device code on the GPU, the debug messages are not nearly as helpful as with traditional programming. So be prepared for long and painful debugging sessions when you use the GPU. And one more thing, this video is actually an experiment from me. I want to try uploading my past talks so that people can watch them even if they didn't see it at a conference. But it's also kind of a different content from what I've been doing lately. Let me know in the comments if you would like to see more of these longer talks or you preferred the shorter content I was releasing before. And either way, if you enjoy my content, subscribe and watch this next video here.